Okay, now we're going to talk about monohybrid crosses, and I'll do several on the board and show you a statistical test for determining if data is really in a specific monohybrid cross or not. I think it's a good idea to keep a list like this of the F2 phenotypic ratios. This shows the 4 for the monohybrid cross we're going to do. We'll also do dihybrid crosses soon in a different Zoom lecture. But I would keep one of these with you when you're working on the problems, and that should help you a lot. Another thing that'll help you with the problems is at the back of each chapter are problem solutions, usually to at least 2 problems worked out in these gray highlighted pages here. This is for the end of chapter 3. So let's get going here. First thing we're going to do is a monohybrid cross with complete dominance. So I'll abbreviate monohybrid cross with complete dominance. Parental generation. Pea plants that have purple flowers. That's the dominant trait. I guess dominant, big A, big A. Cross them. Plants that have white flowers. That's the recessive trait. And so those plants on genotype little a, little a. F1 or first filial generation. Of course, get a big A from the purple parent and a little a from the white parent. And because big A is dominant to little a, all these plants will produce purple flowers. So the recessive trait disappears in the F1 generation, but we'll see it will reappear in the F2 generation. Then we cross F1s, or in the case of plants, we can self them. So the X with the circle around it means selfing. To get the F2 or second filial generation, that shows the characteristic ratios. So in a monohybrid cross with complete dominance, 3/4 of the offspring show the dominant phenotype, purple, and 1/4 show the recessive phenotype, white. So the purple plants all have an A in their genotype, and that dash means that the second allele doesn't matter. It's still the same phenotype. The whites, however, the recessive are homozygous recessive, and they can only be one genotype. If we want to see how we get this using a Punnett square, let's look at that. So here we're crossing 2 heterozygotes, F1s in other words. See here that 3/4 of the offspring will have exhibit the dominant trait and 1/4 the recessive trait, and so that's where we get the 3:1 F2 phenotypic ratio. So we just take the numerator from these 2 fractions, and that is what makes up that ratio. And again, we're not saying that plants produce only 4 offspring, but these are just the 4 ways that the gametes can fertilize each other, and the 4 possibilities. So these aren't absolute numbers, but proportions or fractions. So now let's move on to a monohybrid cross with incomplete dominance. This cross involves a different species of plant. These are plants called 4 o'clocks. They're like small petunias. But anyway, we've got homozygous plants for red flowers, homozygous plants for white flowers. And the genotype of the F1s, of course, is big A, little a, but this time they're not going to be red, they are pink. So here the heterozygotes have a different and distinct phenotype. And then like before, we will self or cross 2 of the F1s together, the F2 generation. The F2s, 1/4 will be red, big A, 1/2 will be pink, big A, little a, and 1/4 will be white, little a. So if we look at go back to our Punnett square here, this guy's red, this guy's white, pink, pink, and this becomes our 1, 1, F2 phenotypic ratio. Characteristic of a monohybrid cross with incomplete or partial dominance. That's 2 of our monohybrid crosses. Let's do a third one now. This one will be concerning lethal alleles. Lethal alleles are often, but not always, recessive. In this case, consider them recessive. So, cross 2 strains of mice called yellow mice. They are heterozygotes. And the C is that 2/3 of the mice will be yellow. Little a, 1/3 will be non-yellow. Big A, yielding our 2-to-1 F2 phenotypic ratio. And so, if we go over a Punnett square, we've got a cross like this, except these guys are non-yellow, these guys yellow, yellow, and those that got the little a genotype were stillborn, so they don't count, of course. So that's how we get this 2-to-1 phenotypic ratio. 2/3 heterozygotes, 1/3 homozygotes. The other homozygote doesn't exist. And so that's our 2-to-1 ratio, indicative of lethal alleles. Okay, now let's look at a test cross. Monohybrid test cross. So thinking about it like Gregor Mendel did, he didn't know about genotypes and so forth. All he knew about was phenotypes. And so if you get yourself a plant that shows a dominant trait like purple flowers, how do you know if it's true breeding or homozygous or not true breeding or heterozygous? Cross it with a homozygous recessive individual. And this individual, by the way, is referred to as the tester. Okay, so assuming this thing is a heterozygote, though, have that genotype, and we could do kind of a punnet column, if you will. These guys are purple, these guys are white, and so we've got half our offspring like that, the other half like that, and so this yields that 1-to-1 F2 typic ratio. It's about equal numbers of each of these two phenotypes. Okay. And so that is the last monohybrid cross that we're going to discuss. Now I'm going to show you a statistical test that you'll need to know to do the problems and to do the exams and so forth. So let's go there now. What's called a chi-squared goodness of fit test. This is the Greek letter chi squared. And in your textbook, it is illustrated on how to do this, pages 68 and 69. Okay. And at the top of the right-hand column of page 68 is the formula. Statistical tests, we distinguish between two hypotheses, H sub naught or the null hypothesis, null meaning 0 meaning no difference, and H sub A the alternate hypothesis. So null hypothesis just states the observed equals the expected. In other words, they're the same. Normally we write it as just O equals E. And the alternate hypothesis, camera bit here, there you go, is the reverse of that, and that just states that O does not equal E. And the results of our test are always framed in the null hypothesis. We say we reject the null hypothesis, or we fail to reject the null hypothesis. Now the chi-square formula listed on page 68. Chi-squared equals the sum of observed minus the expected squared divided expected. And this value that we calculate will we will compare it to a value in table 3.7 at the bottom of page 68 in your textbook. If the value we calculate is bigger than the value in the table, then we reject our null hypothesis. If the value we calculate is smaller than the value in the table, then we say we fail to reject our null hypothesis. Okay? So in the problems, they're going to give you results of the crosses, and you'll have to figure out what type of cross it is based on those results. So here we've crossed some pea plants, tall ones and dwarf ones. And remember, tall is the dominant trait, dwarf is the recessive trait. We got 787 tall plants and 277 dwarf plants. Is 1,064 little baby pea plants. So this is our data, or our observed numbers. I calculate this chi-square value as a table. So can we see everything? Okay, let me move the camera a little bit here. Okay, there we go. Our next row is our expected proportions. Given that we just have two phenotypic categories, one's about 3 times bigger than the other, we think this is probably a monohybrid cross with complete dominance. Therefore, 3/4 of the offspring ought to be tall, and 1/4 ought to be dwarf. One thing we need to do is calculate an observed ratio. That we calculate simply by dividing both numbers by the smaller number, 277, and this gives us a 2.84:1 ratio. The 1, of course, comes from dividing 277 by itself. 277 goes into 787 2.84 times. So you can see this is close to 3:1, but it's not exactly 3:1, right? So the test, the chi-square test here will tell us if this is so different from a 3:1 ratio that this is not indicative of a monohybrid cross with complete dominance, or if it is similar enough to assume that it is indicative of a 3:1 ratio. Okay? And of course, our expected ratio is that what the theory of daily genetics gives us, and that's of course a 3:1 ratio, that for a monohybrid cross with complete dominance. Okay, let's go back to our calculations here then. So our next row is our expected numbers. To get those, we multiply the proportions by the total. Okay, so in other words, we're saying 3/4 of 1,064 is, in this case, 798. And 1/4 times 1,064 is 266. And then we add those up. Two totals should be the same, of course. If they're off by 1, that's okay due to rounding. If they're off by more than that, that means you probably made some kind of a mistake. People often want to multiply the fraction by the number above it, but remember, you need to multiply it by the total. Okay, then the next step in calculating our chi-square value is to subtract the expected from the observed. So 787 minus 798 minus 11. 277 minus 266 is 11. And these numbers usually aren't usually the same in the different columns. It just works out this way in this example. Doesn't mean anything. Then We square them. This gets rid of the negatives, but we square them regardless of whether there's negatives or not. And so 11 squared minus 11 squared is 121. 11 squared is 121. And then to numbers smaller again, we take the squared numbers and divide them by the expected. So 121 divided by 798 in this column, 121 divided by 266 in this column. And that gives us a 0.15 in the first column and a 0.45 in the second column. And then we add across the columns. That's what this symbol means, capital sigma for summation. And so we add those two up, and that gives us 0.6, and that is our squared sub c for calculated value. Now we have to compare it to one in the table, but the table has rows and columns, so we'll have to figure out which column and which row to use. Let's look at that now. The rows are called degrees of freedom, or DF. And this is something we have to calculate each time we do the test. So it's our number of phenotypes minus 1. So of course, here is 1. So our phenotypes in this case are tall and dwarf, just 2 phenotypes. Subtract 1 from that, so our degree of freedom is 1, so that means we use the top row in the table. Now the column we always used. Columns are called alpha, and I'll define that in a second, but we always use the 0.05 column, and it just happens to be highlighted in your textbook, as you can see here on the bottom of page 68, this column here. Always use that column. And alpha means the probability of making what statisticians call a type 1 error. Probability of a type 1 error. This is like saying 5% of the time we're allowing for a type 1 error, and in a type 1 error, this would be reject 8 sub naught, the null hypothesis, when 8 sub naught is true. Remember here, we're dealing with probabilities, not exact numbers, okay? So probabilities. So this means from that 0.05 column and the top row, our chi-square t value, t for table, 0.841. Okay. Now, if the value we calculated is bigger than that, we reject the null hypothesis and say that a 2.84 to 1 ratio is not indicative of a 3 to 1 ratio. Or if the value we calculated is smaller than that value, then we say that we fail to reject the null hypothesis and our data is indicative of a 3 to 1 ratio. And so in this case, we say that we fail to reject some naught. Okay. So make sure you can see that. That's our results. Fail to reject the null hypothesis. So that means our observed and expected are essentially equivalent. And that is all for monohybrid crosses. If you have any questions, please contact me. And goodbye.